In this video, we're going to discuss quadratic spline interpolation. So for quadratic spline interpolation, we will present two possible interpolation schemes. In scheme 1, the intervals between the data points are used as the intervals on which the quadratic functions are defined. In scheme 2, the intervals where the quadratic interpolation functions are defined are chosen different from the intervals between the data points in a way that ensures symmetry of the quadratic interpolation. So let's first consider scheme 1, where the intervals between the data points are used as the intervals on which the quadratic function are defined. So consider a set of k data points with k-1 intervals between the data points x1, y1, x2, y2, up to xk, yk. We aim to find a quadratic polynomial of the form si of x is equal to ai plus bix plus ci x squared on each interval from xi to xi plus 1. So we can see here a graphical representation of what we're doing. So the y values here are the data points with their corresponding x values up to yk and xk. So the first interval goes from x1 to x2, and within that interval we have a quadratic function defined as a1 plus b1x plus c1x squared. Similarly, for the interval 2, we have another quadratic function, interval 3, another quadratic function, up to interval k-1, where again we have another quadratic function, a k-1 plus b k-1x plus c k-1x squared. So the k data points surround k-1 intervals. On each interval I, there is a parabola. Si of x is equal to ai plus bix plus cix squared, with three unknowns ai, bi, and ci. So the number of unknowns is 3 unknowns per interval times k-1 intervals, so 3 times k-1 unknowns. So with 3 k-1 unknowns, we need 3 k-1 equations to solve for our unknown coefficients. And we can get these by specifying a number of conditions. So first, the function values of adjacent polynomials must be equal at the interior knots. This ensures that the splines pass through the data points and ensures continuity of the splines. So if we look at our intervals here, at all of the interior knots as shown here, we have to have that the function values have to be equal, and they have to be equal to our data point. So we can write this as si minus 1 of xi is equal to si at xi, and they're both equal to yi. And we can write this in terms of our the form of our equations and get this in terms of our a's and b's and c's. So this gives us 2 k-4 equations for the interior knots. Similar to this, the first and last functions must also pass through the endpoints. So this means that at x1, the function has to pass through y1, and at xk, the function has to pass through yk. So this gives us 2 additional equations as shown here, where we've got s1 at x1 is equal to y1, and s of k-1 at xk is equal to yk. So again, this gives us 2 additional equations for the end knots. So if we add that to our previous number of equations, now we have 2 k-1 equations. So the next condition that we can specify is that the first derivatives at the interior knots must be equal. This ensures that the connection between the splines is smooth, so the first derivative is continuous. So we can write this as shown here. So basically, the derivative of this function has to be equal to the derivative of this function at the point that they meet at that knot. So the first derivative of si at xi plus 1 is equal to the first derivative of si plus 1 at the same point xi plus 1. So we can write this in terms of our coefficients, and you can see that the a's don't appear in these equations as we take the derivative of the form of our equation. So this gives us an additional k-2 equations. So this added to our previous ones, we see that we need one more equation. So there are a number of things that we can do to get this last equation, and here we assume that the second derivative at the starting point is equal to 0. So this means that the first 2 points will be connected by a straight line. So the second derivative of s1 evaluated at x1 is equal to 0. So this means that 2c1 is equal to 0, or c1 is equal to 0. So now we had two k minus 1 equations from assuming continuity at the nodes. We had k minus 2 equations assuming the first derivative was continuous, and now we're adding this one equation by setting the second derivative equal to 0 at the first interval, or the starting point. So this gives us 3 k minus 1 equations to solve for our 3 k minus 1 unknown coefficients. So the resulting equations are shown here. So these ones come from the continuity at the nodes, including both the endpoints. And then these ones come from setting the first derivatives equal at the knots. And then this last one comes from setting the second derivative equal to 0 at the starting point. So let's take a look at an example using this scheme of the quadratic interpolation to find an interpolating function between these 4 data points. So there are 4 data points, which means k is equal to 4, and we have 3 intervals, so k minus 1 is equal to 3. So that means there are 3 times k minus 1, which is equal to 9 unknowns. So these are the 9 equations that we get according to scheme 1 that can be solved for our 9 unknowns. So again, these ones come from the continuity equations. These come from the first derivative, and this comes from the second derivative at the starting point. This can be written in matrix form as a matrix of constant coefficient or constants multiplied by our unknown coefficients is equal to a constant. So it's a linear system of equations. So we can solve this using some of the methods that we talked about in the previous chapters, or we can also use some of the built-in functions in MATLAB to solve this. And if we do, we get the values of the coefficients shown here. So as you can see, C1 is equal to 0 by construction. And the resulting interpolating spline is shown here. So we had 4 data points, so we had 3 intervals. So we had 3 different interpolating polynomials as shown here with our 3 different sets of coefficients. And you can see that the function passes through the data points and gives us a nice smooth curve. Now there are disadvantages to this scheme of the quadratic spline interpolation. In certain cases, such as fluctuating data, this scheme might lead to some oscillations within the intervals between the data points. So for an example, we can extend this, those first 4 data points were taken from the Runge function, we can extend this to the 11 data points that we've considered in previous examples, and you can see the resulting interpolation shown here. So the yellow line is the original function and the blue line is the interpolating function with our quadratic splines using scheme 1. So you can see that it follows the original function in the first intervals, but at the later intervals we see that there are large oscillations, which would give erroneous results if we use this to interpolate the data. So for scheme 2, intervals where the quadratic interpolation functions are defined differently from intervals between the data points. So this scheme provides symmetry in the interpolation function, which you can see did not exist in the previous scheme, as in the example shown with the Runge function. So let's consider the set of k data points as usual, x1, y1, x2, y2 up to xk, yk. So our new k minus 2 intervals, where the piecewise quadratic functions are going to be defined, are bounded by the points shown here. So we keep the same data points at the end, but then the interior points are defined as the average of the 2 given data points. So x2 plus x3 over 2 up to xk minus 2 plus xk minus 1 over 2. And on each of these k minus 2 intervals, we define a quadratic polynomial of the form si is equal to ai plus bix plus cix squared. So this can be seen graphically here. So we still have our same data points, y1 or y2, x2, y3, x3, but our intervals are defined differently. So at the beginning, we do keep the same endpoints, but then the other end of that interval is the midpoint between the two given data points. So this whole area here is defined by one function, and then this whole area is defined by the next function. So with k data points, we get k minus 2 quadratic functions defined on our k minus 2 intervals between the new set of points that we define. So the number of unknowns is 3 unknowns per quadratic function times k minus 2 intervals, so 3 times k minus 2 unknowns. So that means we need 3 times k minus 2 equations to solve for our unknown coefficients. And again, we can get these by defining various conditions. So first, the quadratic polynomials have to pass through the k data points. So this gives us k equations. Second, the quadratic polynomials have to be continuous and differentiable at the k minus 3 interior points that are the bounds of the intervals. So this gives us an additional 2 times k minus 3 equations. And if we add these together, we see that we get 3 times k minus 2 equations in total, so that's enough to solve for our unknown coefficients. So the resulting equations are shown here. So these ones come from the condition that the functions have to pass through all of the data points, and then these ones come from the conditions that that the functions have to be continuous and differentiable at the connection between the functions, the interior data points. So let's look at an example and use scheme 2 of the quadratic interpolation to find the interpolating function between the following 5 data points. So we have 5 data points, so that means we have k is equal to 5, and the k minus 2 equals 3 intervals for the quadratic interpolation functions are defined between the points minus 1 to minus 0.7, and then up to minus 0.5, and then to minus 0.2. So we keep the given data points at the ends, and then we recalculate the interior endpoints of our intervals. So this means there are 3 times k minus 2, which is 9 unknowns. So the 9 equations developed according to scheme 2 are shown here. So the first ones come from the setting that the functions have to pass through the data points, and then these come from setting that the equations have to be continuous at the internal interval endpoints, and then this is that the first derivatives have to be continuous at the internal interval endpoints. So in matrix form, this we can write this out in matrix form and solve this to find our unknown coefficients a1, b1, c1 up to a3, b3, c3. And the resulting interpolating spline is shown here. So you can see that our first function is defined from minus 1 to minus 0.7. Our second one is from minus 0.7 to minus 0.5. And our third one is from minus 0.5 to minus 0.2. And you can see that it passes through the functions and it gives us a nice smooth curve again. And here we can apply this to the 11 points of the Runge function, showing that the scheme is actually able to remove the oscillations compared to scheme 1 and produces a nice symmetric interpolating function.